Good morning, students. I welcome you all for another session of this numerical problems. Okay, so one more problem we're going to consider today. So the problem is like this: a rectangular section 230 mm into 500 mm is used as a simply supported beam for effective span of 6 meter. The beam consists of tensile reinforcement of 4000 mm square and center of tensile reinforcement is placed at 35 mm from the bottom edge. What maximum total UDL can be allowed on the beam? So how much UDL, that is maximum UDL, can be allowed on the beam, that we need to find out. Use M20 grade concrete and Fe 415 steel. So as usual, we are going to draw the cross section of the beam, that is width of beam B, then overall depth. Now see, this is 500 mm is the overall depth, capital D. So from this to this bottom 500 mm. Now we need to find out the small d, effective depth you have to find out, that is from top to the center of reinforcement. This is not given, but what they have mentioned here, right? Center of tensile reinforcement is placed at 35 mm from the bottom edge. See, from the bottom edge of the beam, okay, at a distance of 35 mm, there will be this reinforcement center. Okay, from bottom to the center of reinforcement is 35 mm. So this is called as effective cover. Okay, this is called as effective cover. So in beam, we cannot place these steel bars directly on the bottom. So there should be some gap at the bottom. So that gap is called as cover. So cover is always required for the reinforcement. So in this problem, it is given that the steel bars center of tensile reinforcement is at 35 mm from the bottom. So from bottom to center of this will be 35, and this is called as effective cover. So capital D, that is overall depth, minus this effective cover will give from top to center, that is called as effective depth. So effective depth is equal to D minus effective cover, that is 500 minus 35, that is 465 mm. Make this correction, it is 465 mm. Okay, then similarly length of the beam, that is effective span of the beam, is given 6 meter. Okay, and as usual, area of steel 4000 mm square. Then characteristic compressive strength FCK 20 Newton per mm square, that is M20 grade concrete, and Fe 415 grade steel means Fy is equal to 415 Newton per mm square. So as usual, first step, actual depth of neutral axis, that is XU. So we are going to find out using this expression, that is XU by D is equal to 0.87 Fy AST divided by 0.36 FCK B into D. So find out this XU by D substituting all the values. Area of steel, okay, then Fe 415, that is 415 Newton per mm square, FCK 20, width of beam, and effective depth of the beam. Substitute all these values, we will get XU by D 1.87, that is actual depth of neutral axis, XU, that is, or XU by D is equal to 1.87. Similarly, next step, we are going to find out the limiting depth of neutral axis. Okay, limiting depth of neutral axis, that is XU limit or XU max, both are same. So as you know, what is the grade of steel? Fe 415 grade steel. For this grade of steel, what will be the XU max upon D value? XU max upon D is equal to 0.48 directly. So even you can refer this in IS 456 2000 code book. So XU max upon D is equal to 0.48 for this grade. So now there are two values now, XU by D value and XU max upon D value. So compare these two, right? So comparing XU by D with XU max upon D will get, so since XU by D is greater than XU max, in this case XU by D value is greater than XU max upon D, so the section is over reinforced. Remember, this is important now. So if this is more than this, the section is, or beam is, over reinforced beam. So when it is over reinforced section, then we need to find out ultimate moment of resistance, MU limit, not MU. For under reinforced section, we will find out MU, but for limiting condition or over info section, we're going to find out mu limit. Okay, now directly we can use, now again see the grade of steel. What is the grade of steel? Fe415 grade steel. Okay, for this grade steel, directly we can write this expression. Right, for Fe415 grade steel, what is mu limit? Mu limit is equal to 0.138 FCK BD square directly. So mu limit 0.138 FCK BD square. So 0.138 FCK 20, B is 230 and small d effective depth 465 square. So calculate mu limit, which comes out 137.26 into 10 raised to 6 Newton mm. Okay, 137.26 into 10 raised to 6 Newton mm. So if you convert this is in kilonewton meter, convert Newton to kilonewton. Okay, divided by 10 to the power of 3, that becomes kilonewton. Then again millimeter to meter, mm to meter, again divided by 10 to the power of 3, means, so this total value, that is 137.26 into 10 to the power of 6 divided by 10 to the power of 6, these two get cancelled. So what is remaining? 137.26. Now it is kilonewton meter. Kilonewton meter. Instead of Newton mm, it is kilonewton meter. Okay, so this is the ultimate moment of resistance, means the beam will going to resist how much moment? 137.26 kilonewton meter. Okay, so this is the moment of resistance given by the beam. Now what they have asked in the problem, we have to find out what is the maximum total UDL can be allowed on the beam. Okay, right, what is the maximum total UDL that can be allowed on the beam. Now this is the ultimate moment. Okay, this is ultimate moment. Now this divided by 1.5, what will going to give? Working moment. This is mu means ultimate moment, m means working moment. So working moment of resistance, m is equal to this mu limit divided by 1.5. Okay, this value divided by 1.5 will give m, that is working moment of resistance. So m is equal to mu limit divided by 1.5, we will get m is equal to 91.5 kilonewton meter. 91.51 kilonewton meter. This is mu limit. Now it is m, working moment of resistance. Now next, now see the beam section. It is given that a rectangular section which is simply supported beam. Now see, this is a beam simply supported over two supports and it is subjected to UDL. Right? So what is the intensity of UDL? It is W per unit length. This W only we have to find out. So what is the value of W? So this is the UDL subjected coming on the beam. So because of this beam, because of this UDL, okay, there will be a bending moment. There will be a bending moment on the beam. Now see, what is the maximum bending moment for simply supported beam? This is simply supported beam carrying a UDL. So if the simply supported beam subjected to UDL completely, what is the maximum bending moment? Maximum bending moment will be WL square by 8. Okay, for simply supported beam subjected to UDL, maximum bending moment will be WL square by 8. Now there are two values now. This is the bending moment coming on the beam and this is the resistance given by the beam. So equate these two. So these two must be same. So equating maximum bending moment, this is maximum bending moment to moment of resistance m. So therefore m max is equal to this, m max is equal to m. So m max is WL square by 8, that is equal to m is 91.5 on kilonewton meter. So substitute all the values. WL, this is the span, effective span from center of this support to the center of this support, effective span is given 6 meter. So WL square, W 6 square divided by 8. So that is equal to 91.51. So W into 6 square is equal to 91.5 into 8. So therefore you can calculate W is equal to how much? 20.34 kilonewton per meter, okay, including self weight. So whatever this UDL, what we are seeing this UDL, okay, the value of UDL is how much? 20.34 kilonewton per meter. Means for 1 meter, what is the value of W? It is 20.34 kilonewton. So this total UDL including self weight, okay. So this UDL includes self weight of beam also, live load, okay, live load plus self weight of the beam. That's the total UDL will be 20.34 kilonewton per meter. So this is what the result they have asked in the problem. So this is the total UDL which can be allowed on the beam section, okay. So this is an important problem. Please solve this problem once again, okay, and if you have any doubts, feel free to ask me. So we'll come up with some more problems in the next session. So thank you very much for attending this session. Thank you.